In today's lecture, you will learn how to perform the convergence of Markov-Chain Monte Carlo. And this convergence issue is very crucial because if we don't have convergence, then the validity of the posterior inference is questionable. That means it's really invalid. And you will learn different types of convergence diagnostics. Next, we'll talk about MCMC convergence, because this is again very important. Once we get the MCMC sample, how do you know that the samples converged to some true posterior distribution? So diagnostic measure for MCMC convergence has become very important. So the point is, after the model has converged, samples from the conditional distributions are used to summarize the posterior distribution of parameters of interest theta. Convergence refers to the idea that eventually the gift sampler or other MCMC technique that we choose will eventually reach a stationary distribution. From this point onwards, it stays in this distribution and moved about or mixes throughout the subspace forever. The general questions for us are: 1. At what point do we know that we have converged to the stationary distribution? That is, how long should our burn-in period be? And number 2, the second point, is after we have reached the stationary distribution, how many iterations will it take to summarize the posterior distribution? The answers to both of these questions remain a bit ad hoc because the desirable results that we depend on are only true asymptotically, and we do not want to wait for an infinite number of draws. So what are the possible problems with MCMC? The assumed model may not be realistic from a substantive point of view or may not fit. Errors in calculation or programming, often simple syntax mistakes, may be responsible. However, it is possible that the algorithm may not converge to a proper distribution. Slow convergence. This is the problem we are almost likely to run into. The simulation can remain for many iterations in a region heavily influenced by the starting distribution. If the iterations are used to summarize the target distribution, they can yield falsely precise estimates. This will be the focus of our discussion. We use different techniques. First is the trace plot. So what's the trace plot and what it does? Let me explain that. One intuitive and easily implemented diagnostic tool is the trace plot or history plot, which plots the parameter value at time t against the iteration number. If the model has converged, the trace plot will snake around the mode of the distribution. A clear sign of non-convergence with a trace plot occurs when we observe some trending in the sample space. The problem with trace plots is that it may appear that we have converged. However, the chain trapped for a finite time in a local region, rather exploring the full posterior. And there are many examples you can create from running real data using the MCMC technique. and those pictures of real data analysis are done in your notes. I strongly encourage you to look at the notes and convince through some of the examples. Then the next measure we'll talk about is the autocorrelation diagnostic. So this comes after the trace plot. Autocorrelation refers to a pattern of serial correlation in the chain, where sequential draws of a parameter, say theta sub 1, from the conditional distribution are correlated. The cause of autocorrelation is that the parameters in our model may be highly correlated, so the gift sampler will be very slow to explore the entire posterior distribution. The reason why autocorrelation is important is that it will take a very long time to explore the entire posterior distribution. Autocorrelation diagnostic. Note that if the level of autocorrelation is high for a parameter of interest, then a trace plot will be a poor diagnostic or convergence. Typically, the level of autocorrelation will decline with an increasing number of lags in the chain. Example, as we go from the 1000 to the 1010 lags, the level of autocorrelation will often decline. When this dampening doesn't occur, then you have a problem and will probably want to reparameterize the model. More on this will be discussed next. So next we'll talk about, again in your notes you will find out some examples of the problem with autocorrelation. Next we'll talk about running means of parameters. The running means, once you have taken enough draws to summarize the posterior distribution, then if the model has converged, further samples from a parameter's posterior distribution should not influence the calculation of the mean. A plot of the average draw from the conditional distribution of draws 1 through t against t is useful for identifying convergence. Note that you could probably get the same effect with a trace plot. Next diagnostic measure is called the kernel density plot. A kernel density plot, which is a smooth density or histogram, may be useful diagnostic. Sometimes non-convergence is reflected in multimodal distribution. This is especially true if the kernel density plot isn't just multimodal but lumpy. When you get a lumpy posterior, it may be important to let the algorithm run a bit longer. Often doing this will allow you to get a much more reasonable summary of the posterior. And there are quite a few examples given which are problematic kernel density plots in your notes. So next we'll talk about Geweke time series diagnostic. The Geweke time series diagnostic tells that if a model has converged, then if simulate a large number of draws, the mean and variance of a parameter's posterior distribution from the first half of the chain will be equal to the mean and variance from the second half of the chain. Technically, this statistic is based on spectral density functions that are beyond the limit of this course, and then Weinberg does not estimate the statistic directly, but if you export the CODA chain to R, the programs CODA and BOA Bayesian output analysis, report the Geweke statistic. However, a perfectly reasonable way to proceed is to look to see whether the posterior means and variances of your parameters are approximately the same for different halves of your simulated chain. The Geweke time series diagnostic tells you if a model has converged, then if you simulate a large number of draws, the mean and variance of parameters of distribution from the first half of chain will be equal to the second half. The value of this approach is that by allowing the algorithm to run for a very long time, it may reach areas of the posterior distribution that may not otherwise be reached. Then we'll talk about Gelman-Rubin diagnostic. Gelman especially argues that the best way to identify non-convergence is to simulate multiple sequences for over-dispersed starting points. The intuition is that the behavior of all of the chains should be basically the same, or as Gelman and Rubin put it, the variance within the chains should be same as the variance across the chains. I think this can be diagnosed pretty easily through trace plots of multiple chains. You want to see if it looks like the mean and the variance of the two chains are same. Again, in the notes you find examples where convergence seems reasonable. That is, the mixing happens pretty well. The Gelman-Rubin diagnostic statistic is based on the following procedure. We estimate the model with a variety of different initial values and iterate for an n iteration burn-in and an n iteration monitored period. We take the n monitored draws of m parameters and calculate the statistic. One is within chain variance, then between the chain variance, we estimate the variance v hat theta, and then Gelman-Rubin statistic defined as square root of r is square root of v hat theta divided by w. The detailed formulas are given in your notes. Some fine points. Before convergence, W underestimates total posterior variance in theta because it has not fully explored the target distribution. V theta, on the other hand, overestimates variance in theta because the starting points are over-dispersed relative to the target. Once convergence is reached, W and V theta should be almost equivalent because variation within the chains and variation between the chains should coincide. So R should approximately be equal to 1. The drawback of this statistic is that its value depends on a great deal on the choice of initial values. So finally, we summarize our convergence diagnostics. We can never prove that something has converged. We can only tell when something has not converged. If your model has not converged and you are confident that you have not made any mistake, then the best thing is to just let the model run a long time. CPU time is often cheaper than your time. For models with large numbers of parameters, you should let model run for a long time. There are a number of easy ways to implement tricks, mostly reparameterizations, that will help to speed convergence in most regression-based models. Convergence does not mean that you have a good model. Convergence should be the beginning of model assessment, not its end. So in this module, you have learned how to perform different types of convergence diagnostics of Markov chain Monte Carlo method. You have learned in particular Gelman diagnostic, Geweke convergence diagnostic, Traceplot, and various other things. These are really crucial for performance of the Markov chain Monte Carlo method.